Hello there, my lovely physical science students. We're going to finish our section 1 notes, as it says right here. So let's go ahead and get started. These are going to be the PowerPoint notes, just like what you have in class. So as I scroll through them, it would be just like what you would have in class. It's just you're only going to hear me talking as opposed to see me. So first thing, at the beginning of your notes, you do want to write down the goals of the day. So our first goal, describe the changes seen in matter during a thermal expansion. Now I might talk a little bit quicker through these notes than I would in class, so that if at any time you need to pause it in order to get the information written down from the slide, you can always hit the pause button and then push play. The second goal that we're going to discuss is explain the unusual behavior of an amorphous solid and a liquid crystals. So first thing we're going to talk about is something called thermal expansion. So anytime we have an increase in the size of a substance when the temperature is increased. So for example, we heat up objects, they're going to expand in size. So example would be, concrete. A lot of times they put what they call lines in the roads to allow for some sort of expansion to occur. This does occur in most solids, liquids, and gases. So sometimes people only think, oh, well, solids expand. Well, yes, liquids expand as well. A really good example of a liquid expanding would be our water. All right, so again, a really good example for our liquid, a really good example for that is ice is going to expand, all right, when it's frozen. Or I should say, water expands when it actually freezes. So ice is always going to get a little bit bigger than the liquid was. So example of concrete, they have to put a line down the middle of it. And I'll show you a couple pictures. Let me get past these few things. Let's look at the pictures, and I'll come back to those two things. So here we can see, this is what we might see in a bridge. So notice that there's all these little finger-like projections that are, separating the concrete. This allows for the road to actually expand in the summertime. So when things get hot, they expand. So these little teeth actually begin to move apart from one another. So in the summertime, these things would actually expand and spread out. In the wintertime, the opposite's going to happen. So in the wintertime, these little teeth are actually going to move together in the winter because things are going to contract when they get cold. So in the summer we have expansion, and in the winter we're going to have some kind of constriction going on. If we did not have these special lines put into our bridges would collapse because they would crack and break and basically fall apart. So these allow for the road to be able to expand and contract whenever we go through different months of summer and of winter. So let's go back and look at the couple things then. So thermal expansion is explained by our kinetic theory. So just a reminder, kinetic theory always deals with particles that are in motion. So our kinetic theory means when our particles speed up, when our temperature is raised, when they speed up, they bump into each other more often, and it causes them to spread out even more. So something to think about for our kinetic theory is to think about when you get burnt. So you have a hot stove. All right, here's the hot stove coil on our stove. And let's say you accidentally touch that hot stove. Ouch, you're going to get burnt. What happens to your finger when you get burnt? You get a blister. So on your finger then, where you touched, you get some kind of blister starting to form. Blisters are just the expansion of your finger. The gases, the liquids inside your finger are trying to push themselves outward. Well, your skin is a little bit elastic, and it allows for it to actually bubble up and actually have a blister. Think of it as blowing up a balloon. You increase the gas, so it's going to make it larger. Blisters work exactly the same way. So for this first one, I'm just going to add the little equal sign after it like I have for the next one. And we're going to say this equals expansion. The next part I put down, particles are going to slow down when our temperatures are low. Because they slow down, they're going to move less. So our particles slow down when temperatures are low. Therefore, they are closer together, so we get contraction. So think of this as my particles are going to slow down. When they slow down, they can start to actually get closer together then. So there's our pictures of our road again and the bridge. So you can see here, this big, large, looks like, oh wow, the bridge is cracking and going to fall apart. No, the engineers have actually designed this so that the concrete can actually contract and expand during our winter and our summer months. All right, we not only have expansions of solids, we also have expansion of liquids. One real good example, a thermometer. When you add energy to a thermometer, it causes the liquid particles to start to move faster. Anytime something starts to move faster, it's going to cause expansion to happen. Where does the liquid inside a thermometer go? But up. So when our thermometer's temperature starts to heat up, so when our temperature rises, the liquid inside has only one place to go, so the liquid is also rises. So our temperature raises, our liquid raises. And like a day like today where it's very cold, you might see that temperature starting to really drop down. So when the temperature drops down, thermometer goes down because our particles can now sit closer to each other. Expansion of gases. So we had expansion of solids, expansion of liquids, and now we can, yes, expand the gases as well. So gases also expand when heated. Example, good real world example is a hot air balloon. When we want to go up in a hot air balloon, we have to heat the gas. So if we want to go up in a balloon, we need to make the gas hot. By making the gases hotter, we're causing all of the molecules inside the balloon to start literally beating into the balloon itself. That extra added energy of the balloon being hit by all these molecules cause our balloon to actually rise up into the sky. When we want to come back down, we just cool the gases back down. Amorphous solids. So first of all, you're probably thinking, okay, amorphous is a weird word. It is. Amorphous just means it's not normal. Something is different about this solid than every other solid. So first thing, not all solids are going to have a definite temperature of melting and boiling. So these types of solids don't necessarily melt and boil at the same temperatures that other solids might. So one example, water. We know water's melting point. We know water's boiling point. That's something that any water is going to have. Amorphous solid, on the other hand, are going to have different melting points and boiling points, even if it's the same amorphous solid. So these are solids that are going to lack that rigid structure that we see in other solids. So as we drew the picture today on the board, we said in a container, our solids are going to stack up very nicely, all going to be in rows, very neat and orderly, all the same size, even though my circles may not look exactly the same size. But notice everything is stacked one on top of each other. Nice, rigid, orderly. Think of classroom desks. In most classes, there are certain rows that are always nice and straight, and then the columns that are going across. Everything is nice and neat and orderly. These types of solids, amorphous solids, are not orderly. They lack that rigid structure. So examples of this, glass and plastic, are both amorphous types of solids. What they do to make glass and plastic is they form chain-like structures, so chemically they make chains, that create the appearance of a solid by jumbling them up like a big ball of string. So to create these solids, they take all these different strings. So if you think of stringing together all this stuff, it has no real random pattern. Big ball of string. Now take two pieces of matter and squish it together so that what you have is all this jumbled up stuff now squished together so that it actually starts to appear like it's a very solid structure when in fact it's not. It's able to move and bend because it's made up of all these squiggly, jumbled up pieces like a big ball of string. Last one, liquid crystals. Right now, technically, you are staring into a liquid crystal because you're watching this on either your phone, which is a liquid crystal screen, or your computer screen. So here, the geometric arrangement of particles are kept when the substance is a liquid. So this is something that they actually flow. So when they make computer monitors, the screen that's used to make the screen that you're looking at right now, think of this as it's a flowy liquid sheet that flows out into big giant sheets. So instead of when you pour a liquid out, it's going to pour out into a single drip. This will literally pour out into a big giant sheet that when they make computers, then they just cut the sheet. So this part here would be a computer screen for one. They cut the sheet again. Here's another computer screen. So it flows out kind of like a liquid, but it's kind of like a solid too. Examples of places you would find these. LCD stands for liquid crystal diodes. So anything you have that says it's an LCD screen is made out of these liquid crystals. Watches, if you have a watch screen or a watch that is the digital kind of watch. Clocks that are digital and digital calculators are all going to have some kind of LCD screen to them. All right, hopefully everything went well with this. Remember, you could have always stopped, paused, rewind. You can rewatch as many times as you would like. So your homework tonight is still to do the page 483, page 483, 1 through 5. Hopefully this was pretty good for you, and I'll see you guys tomorrow. Bye-bye.